Okay, so today, whole new topic, whole new transform, Z-transforms. No, not that kind of Z-transform. No. These are very cool transforms. So, again, the question always comes up. We've got such a great thing going with discrete-time Fourier transform. Why do we need another one? What's the motivation here? And if you think back to continuous time systems, we're going to make all the same arguments we did that took us from Fourier transforms to the continuous time equivalent of Z-transforms, which is the Laplace transforms. So Laplace domain and the Z domain are kind of parallels between the continuous time system and the discrete time system. So all the limitations and reasons for why we developed the Laplace transform, and even the method that we used to develop Laplace transforms from Fourier, will again be done in its discrete form when we go to Z transforms here. So while the DTFT is really useful, it lets us look at the spectrum, the signal content of signals. We like that. We want to keep that. For terms of system analysis, it only gives us a way to do convolution, which means I can only operate with relaxed systems. I don't have any way to find zero input responses. All I can do is find zero state response. So you give me some initial conditions and I can't work with them. I can't give you their contribution to the total system response. And there are a lot of real world situations where we'll have initial conditions and we have to work with them. We have initial charges on capacitors, we have magnetic fields already established around inductors. What do we do then? Well, we can't solve for those parts of the response using either convolution or Fourier transforms. So right now all we could do is try to solve a differential equation with those initial conditions, and that's still too much work. So we want something that's going to take the place of that for us. The DTFT also is a little bit complicated in appearance, right? There's E to the J stuff floating all over the place in there. As soon as I whip out the transform, I'm going to have some complex exponentials in there. And let's face it, complex exponentials can be scary. They shouldn't be. And there's a whole class of signals or system responses that there is not a valid DTFT for. There's not a valid discrete-time Fourier transform, because the transform itself relies on whatever function we're using has to itself converge in order for the transform to converge. So if I have any like a growing exponential, a growing causal exponential, I can't find a discrete time Fourier transform for it. But I might want to see how a system would respond to that over some finite period of time. So what am I going to do then? Well, Z-transforms to the rescue. They're going to do it for us, just like Laplace did. It broadened the category of signals that we could look at that would have valid transforms. We'll be able to do that with Z-transforms as well. So that's the whys. So how do we remove these shortcomings, particularly that one big shortcoming that the DTFT is not defined for certain signals? Again, that's the problem, because we're doing a summation, an infinite summation. Well, that's a little scary. At least the thing I'm multiplying my function by, we've proven has a magnitude of 1, so that's not going to affect really the convergence of the transform. It's the function itself, h of n, has to sum up to a finite value in order for this transform summation to even be a finite value. And so that's why we impose it had to have an absolutely summable h of n. So that transform only converges if whatever function we're transforming converges. So what we're going to do is kind of the same thing we did for Laplace. We're going to say, all right, if you dare to diverge, I'm going to multiply you by a function that converges, that is going to force the product to go towards 0. So I'm going to try to overpower you with a bigger function that's decaying faster than you were expanding, and make the product go to 0, and then take the transform of that and see what I get. So for example, we're going to use the factor r to the minus n. So if we use r as a whole number value, like 2, that's the minus 1 as a fraction. or to minus n as a fraction. So we start rattling off values like 1, 1/2, 1/4, 1/8. We have an exponentially decaying converging function multiplying another function. If one's diverging exponentially and one's converging exponentially, if I choose my exponential functions right, I can turn that one around and make the product converge. So that's what we're going to do. So let's plug into the DTFT formula, h of n e to the minus j 2 pi n f. We're going to add that converging function r to the minus n. That's all we've done. We kept the rest of the Fourier transform. But now let me regroup this in a way. I've got r to the minus n here. I've got e to the minus n here. So let me take minus n out as an exponent for the whole quantity. And I have a new quantity r e to the plus j 2 pi f. And now I'm going to make a substitution of variables. I'm going to say, let's define some new variable. I'm going to call it z. And z is going to be exactly r e to the j 2 pi f. This thing in red. And so now I have a new transform that was just the Fourier transform with this extra converging function, the sum from n equals minus infinity to plus infinity, whatever the time sequence was that I'm trying to transform, times z to the minus n. How simple is that? No exponentials in there, no complex things in there. Well, actually, both are in there. We're just hiding them, right? Because z is a complex value, r e to the j 2 pi f, which we could interpret as a magnitude and phase for a complex value. It has a real and our imaginary part. But okay, it's all right. That's our new transform. That's the two-sided z transform, or the bilateral z transform. Called that because the summation goes from minus infinity to plus infinity. If I was transforming a causal signal, I only need the sum from 0 to infinity, and we would call that a one-sided transform. Okay. Everybody see the argument? We're going to force it to converge. Now, just like with Laplace transforms, this is going to make my life better. I'm going to be able to make more things converge, but now I got to tell you how I'm doing it. I got to tell you what values of z am I using, or am I allowed to use, so that this transform summation now does converge, because it won't for any value of z. Okay? And those values of z that work, those that make this summation sum to a finite value, those, all that constellation of z values we call the region of convergence. Same terminology we use for S in the Laplace transform. We had a region of convergence there as well. So because we played the same trick, we forced it to converge with a converging function, just like with the S domain, we've got now a region of convergence in the Z domain. Well, let's apply it to a simple FIR filter. Because it's trivial for us to find the unit sample response of this particular filter, we can pick it off from the EK coefficients, the multiplier coefficients in our difference equation. It would be just, well, minus 1/2, 1, minus 1/2. And notice there's an error in the slide, and also probably in your notes there should be a minus sign there, which I thought I fixed, but apparently I didn't. So it should be a minus 1/2 there. But the values are minus 1/2, 1, minus 1/2, for n equals 0, 1, and 2. All right. If I wanted to know what's the z transform of that function, of that unit sample response, well, the DTFT was easy. We just transformed each of these terms. The minus 1/2 times delta of n gave us a minus 1/2. Delta of n minus 1 was a 1 times a time shift property, e to the minus j2 pi f. And this 1/2 delta of n minus 2 gave us a 1/2 e to the minus j4 pi f, where we recognize these e to the minus j, 2 pi f's and 4 pi f's. That's how we got, those came from delays. Those were like delay operators in the discrete-time Fourier transform. So we delayed by one sample, gave us e to the minus j2 pi f. Delayed by two samples, we got e to the minus j4 pi f. How about this z transform thing? Well, so everybody comfortable with that, turned in homework on it, we're all, nothing new there. So what we want to do is ground ourselves in stuff we know. There's the DTFT. Now, let's contrast that with the Z-transform. Let's transform this expression using the Z-transform. Well, it's the sum of this function from n equals minus infinity plus infinity times z to the minus n. But this function only has 1, 2, 3 non-zero values. N equals 0, n equals 1, n equals 2. So I can limit that summation from n equals 0 to 2 and actually plug in the 3 values for h of n that I have at those positions. So with the h of 0 times z to the minus 0, 1 times z to the minus 1, h of 2, z to the minus 2, and everything else is 0. This happens to be minus 1/2. H of 1 is 1. H of 2 is minus 1/2 again. And so, well, I think that's it. So here's my Z-transform, minus 1/2 plus 1 z to the minus 1, minus 1/2 z to the minus 2. And notice that in the Z domain, how a delay by one sample gives rise to a z to the minus 1. And a delay by 2 samples gives rise to a z to the minus 2 in the transform. Oh, gee. Didn't we draw delay blocks in our block diagrams as z to the minus 1? That's why. It was a Z operator, delay operation. And when we were finding characteristic equations of our difference equations, we were taking the values down and multiplying by z. Z was our delay operator. Z to the minus 1, z to the minus 2. Oh. So when we were finding the characteristic equation, we were taking the Z transform of half of the left side of the difference equation. But we couldn't tell you that because you didn't know what Z transforms were. We called it the Z operator. Well, it literally was. It was a Z transform that we were doing. We were Z transforming the left side of the difference equation turn by turn. So now when I have a Z to the minus anything, that's how many samples of delay are introduced. So here we have FIR filter. Finding the Z transform was as easy or easier than finding the DTFT. It still had just a finite number of terms. And now I've got the simpler Z instead of carrying around all those U minus J things. So I don't know about you, but I'm liking this better. Questions on anything that's up there? We're kind of seeing where that all came from. All right. So yeah, easier than the DTFT, prettier, simpler, except we got this region of convergence thing. We got to worry about that. Let's do that to a non-causal sequence. So that first one was a causal unit sample response of a system. Let's try it for still a finite length sequence, but let's let it be non-causal. See if that affects anything. So there's a simple signal, 5 different samples. It's 0 everywhere except at these 1, 2, 3, 4, 5 samples that happen to start at n equals minus 2. That's okay. So I've got n equals minus 2, n equals minus 1, 0, 1, and 2. I can still take the Z transform of that. We can write this as this collection of unit sample sequences, where this delta of n plus 2 is advanced by 2, the n plus 1 gives me the advance by 1, and so on. If we take the Z transform, well, again, I only have to sum over the non-zero values, so I only have to go from n equals minus 2 to plus 2. And again, plugging in the actual values of the function and the Z arguments that go with them, we would get this value of x of minus 2 times z to the minus 2, which is plus 2, and x of minus 1 times z to the minus 1, or plus 1, z to the 0, z to the minus 1, z to the minus 2. And we, again, can jump really quickly to the Z transform. There it is, that's it, answer done, of that finite sequence. Only difference that it's being, now that it's non-causal, I have some positive values of z representing the shifting to the left of the 0 axis for my n. So not a big change, just a small change there. We'll come back around to whether that has any implications to things like the region of convergence. But everybody okay with what we did? So we simply took the formula, plugged in the actual values for finite sequence. We could literally plug in the values. And so just like we did with DTFT, we're going to be faced with, when I want to use the Z transform, I need to compute the Z transform. And we always have the same set of choices. Number one is always plug it into the defining summation and crank it out. Well, that's the way we're going to do it today. And then hopefully from after today, we'll never do that again. We'll just look it up in a lookup table. Or apply some properties to it and figure out how to change it so that we can take a lookup table example and modify it a little bit. Well, that's where we're going on Friday. We're going to talk about the properties and the transform table. So you should be getting used to it like the 4th or 5th time we've done this in the last 2 classes. So we're going to follow that same paradigm, that same pattern, and then get to how we apply this transform. For today, though, starting with the basics, getting some basic idea of how this works, and what is this Z thing, and what is the region of convergence. Okay, so what is Z? It is a complex variable. Well, so is S, right? Remember Laplace transform? You had S domain, you had the S plane. I need a better marker. And S was a complex variable. It had a real part that we called sigma, and it had an imaginary part we called j omega. What about this Z thing? Well, we expressed it in polar form as a complex value, r e to the j 2 pi f, where we could think of this 2 pi f thing just as an angle, e to the j theta. And r is the radius, right? Well, we won't call it theta, we'll call it capital omega. Which actually does have significance. It's a digital radian frequency. We could break it up into real imaginary parts in kind of a rectangular form of a complex variable. That's fine too. And so, just as we did in Laplace, talk about an S-plane and look at values of S and regions of convergence in the S-plane and all that good stuff, we're going to do the same thing here in Discrete-Time now with the Z-plane. It's Z-plane, Z-plane. Where this plane is, again, just all the possible values of Z. Z is a complex value. It could be real, so we have a real axis along here. We have an imaginary axis along here. So if Z is real, it's somewhere along here. If it's purely imaginary, it's somewhere along here. Most Z's will be complex, so it'll be around in one of these other quadrants. So the origin is obviously Z equals 0. In this positive imaginary direction, we have plus 1j, plus 2j, plus 3j. Down here, minus j's. We have positive real values along this axis, negative real axis along this part of the axis. And a really, really, really important place in this Z-plane is right here. So special, we give it its own name. We call it a unit circle. It's literally the circle of Z values that have a complex value whose radius is 1. Everywhere we get a radius of 1 is on the unit circle. That means on the real axis, I cross at Z equals plus 1. On the positive imaginary axis, I cross at Z equals plus j. Over here, I cross at Z equals minus 1. And down here, I cross at Z equals minus j. And all the values of Z, at least those who their polar form has a radius of 1, are points fitting on this particular unit circle. Why do I care about that? Well, we'll come back to that in a second. Other values of Z, Z is in general a complex value, so we'll have a real and imaginary part, so we'll be somewhere off either axis. They could have negative real parts. They can have positive, negative j parts. We're going to see, like we did in the S domain, if you have things that are complex, we're probably going to end up seeing their complex conjugates too. Complex values will travel together. And remember, we did stuff like poles and zeros and regions of convergence and stuff like that, and stability and all those kind of good things. in this S-plane? Well, we're going to be able to do all those same things over here. We're going to have poles and zeros again. We're going to have stability criteria based on where those are. The region of convergence will be related to where those poles and zeros are, and we'll be able to get the frequency response out of this as well. So all those good things we were doing there, we're going to be able to do over here. So far it looks like they're the same. Why do I need an S? Why do I need a Z? Well, they're not quite the same. We'll see in a second here. Any Z point, any Z value, we can always express in polar form with some radius and some angle in the kind of R e to the j omega, or omega is an angle kind of notation. And again, the special ones that have R equals 1 are the ones that live on the unit circle. But now, why do I care so much about that unit circle? Well, let's take a look at what we've done here. Discrete-time Fourier transform. Keep me honest here. Summation from n equals minus infinity to plus infinity of, let's use x of n, e to the minus j 2 pi f times n. Done, right? Z transform. Sum from n equals minus infinity to plus infinity, x of n, z to the minus n. All right. I would like to take my h of z or x of z, my z transform of my time function, and I'd like to know if it's a signal, what's its frequency content? So I'd like to be able to compute x of z, and from that find out what is x of f. This is really useful to me, and this is easier to compute. Or if it's a unit sample response, I'd like to find its h of z and find h of f, the frequency response of the system. So I need a way to relate these transforms. I contend you can make these the same. If I make z equal to what? Do I make this the same as that? What can I replace z with in here and end up with this equation?
E to the minus j 2 pi f n.
Don't need the n, I've got an n.
E to the j 2 pi.
E to the plus j 2 pi capital F. So if I have h of z and I want h of f, I can make this substitution and transform the z transform to the discrete-time Fourier transform. What values of z's are these? In polar form, what's their radius? And what's their angle?
2 pi.
So all the points on that unit circle are the points, the values of z that I'm going to plug into h of z or x of z in order to get h of f or h of f. Another way of saying that is, just like back here in Laplace domain when we wanted to go from h of s transfer functions to Fourier transforms to frequency responses, where were we? What s values were we operating at? What did we replace s with to get h of f or h of omega? Which one? J omega. We were walking along the j omega axis. These were the values of s that we were plugging in to find the frequency response. In this case, the values of z we plug in to find the frequency response are the values on the unit circle. And so, oh, now we see our first big difference between s and z. This is a straight line, it goes on forever. This is a circle, it just keeps repeating itself. Well, that's actually a good thing, that's what we need. But they're very different domains. So, if I want to find the Fourier transform or the frequency response, I can go in my Z domain and replace values of Z along this unit circle, all the ones that have a radius of 1. And not only that, I can relate the angle that I'm at to a frequency that I'm operating at, 2 pi f. So if my angle is 0, my 2 pi f equals 0, so this must represent the frequency response at f equals 0. Happens to be, if I want to know what is h of f at f equals 0, that's the same as h of z at z equals 1. Here. If I go up here to z equals plus j, my angle is pi over 2. So 2 pi f, the angle argument has to be pi over 2. That makes f must be a quarter. So if I want to know what's f, what's the h of f at f equals a quarter? H of f at f equals 1/4. That's h of z at z equals plus j. Likewise, over here at z equals -1, the angle is pi, plus or minus. 2 pi f must be pi, so f must be 1/2. So this we would call the Nyquist frequency, is over here. Likewise, if you solve for this point, z at minus j is f of 3/4, or come back this way, minus 1/4. And if I go all the way around and call this angle not 0, but 2 pi, I say this is also f equals 1. And f equals 2, and f equals 3. And so I need a circle to trace out a periodically repeating function, which h of f is, which x of f is. That periodic spectrum is represented by running around this circle over and over again in the z domain. So the h of f is related to h of z. It's a particular subset of h of z. It just happens to be the ones moving along the unit circle. That's amazing. That's good stuff. So we can easily find h of z. We can easily transform it to h of f, do all those good things we were doing with h of f, and eventually we're going to be able to do more with it because we got z along for the ride. Questions? Is it making sense? See the connections? All right. So that means if we can find the z transform of a system's unit sample response, take h of n, find h of z. We're going to call that the transfer function, just like we called h of s that in the continuous time domain. We can get the steady state frequency response by replacing z with 1 e to the j 2 pi f, or just e to the j positive j 2 pi f. And we'll have an expression for h of f. So we can do all the steady state stuff we did before. We'll actually also be able to do convolution for zero state responses using h of z. And we'll eventually, by moving to the one-sided transform and causal signals, we'll be able to deal with initial conditions as well. Okay, so Z transform is it. Just like the Laplace transform was for continuous time systems, this is the big kahuna. This is how we do discrete time analysis, discrete time design. Usually done with Z transforms. When we want to relate it to the real world, we'll bounce it back to Fourier by making that transformation. We'll replace Z with e to the j 2 pi f. Let's see what happens for some analytical versions when we plug them into the formula. Here's a rising exponential, and like 2 to the n u of n. So it's causal, but it's an increasing exponential. And if we went through the trouble of trying to find the discrete time Fourier transform we would get all the way down to the place where we want to use the summation formula, except we would say we can't because we violate the requirement of the summation formula that the thing we're trying to exponentiate has to have a magnitude less than 1, and it's got, in this case, a 2 in it. So we would be thwarted in trying to find a discrete time Fourier transform, and because it doesn't converge all by itself. But here's where the Z transform will work. We can take this function, take its Z transform. So it's just, you let alpha be 2 at 2 to the n u of n, which we can replace the u of n by eliminating the negative indices and start from 0 to infinity. Then that's just 2 to the n z to the minus n. I can factor out the exponentiation. I'll factor it, take the exponent outside, and have 2 to the first times z to the minus 1. Now this quantity I can plug into the summation, the finite summation formula. It's from 0 to infinity of alpha to the n. As long as I keep this quantity, 2z to the minus 1, having a magnitude less than 1. So now I can proceed, but I have to proceed with a caveat. I've got to make sure that this quantity, 2z to the minus 1, has a magnitude less than 1. If I do, then I'll plug this into the formula and say, hey, there's the transform. It's 1 over 1 minus 2z to the minus 1, or multiply through by z to pretty it up, and have z over z minus 2. If I evaluate this requirement I put on myself in order to use the summation formula, if 2z to the minus 1's got to be less than 1, well, that's like 2 over z. So z to the minus 1 has to be less than 1/2. Taking reciprocals, that means z has to be greater than 2. And that's how I get a definition for the region of convergence. That requirement to use the summation formula to make it converge required me to only use values of z that satisfied this requirement, which was this set of requirements which solved to being z values with magnitudes greater than 2. So along with this transform, I have to tell you, there's only certain values of z we're allowed to use with this transform, and has magnitudes greater than 2. So radii, 2 greater than 2. So bigger than 2 on the real axis, or j2 over here, or minus 2, or minus j2. This region out here, going out to infinity, are the allowed values. They're big enough to make that converge. Make sense? Okay. Now here's a seemingly contrived example that has a big point to it. So bear with me for the contrivance. We want to find the Z transform of a negative anti-causal exponential. That sounds like a lot of things you wouldn't want to do on a Wednesday afternoon. It's non-causal, goes backward in time, right? Here's the positive values of n. It's 0 for n equals 0 and infinity, n equals 0 to infinity. That's why we call it anti-causal. It's completely uncausal. It keeps going to n equals minus infinity. It never quite gets to 0. It starts at n equals minus 1. And, well, it's an alpha to the n, but for negative values of n, alpha can be a number greater than 1 and still have it converge. So it's a converging exponential function. That's okay. But going backward in time. And with a negative sign out in front, just because I need it. That's the point. Let's take the Z transform of that. Same setup. Let's replace alpha with 2. We get minus, and I can bring out in front of the summation, 2 to the n, u to the minus n minus 1, z to the minus 1. I get rid of this guy by saying, well, this goes from n equals minus 1 to infinity. So let's limit the summation from minus infinity up to minus 1. And let's pull an n out for the exponent. So I'm raising 2 times z to the minus 1 raised to the n power, summing it over these values. Okay, can't use my formula on that. So we're going to first do a change of variables. Let's replace this n with a new variable k, and let k be minus n. Then this n becomes minus k. The 2z to the minus 1 doesn't change, but if n was minus infinity, k is plus infinity. And if n was minus 1, k is plus 1. So I just rearranged the limits of summation to accommodate that change of variable. All right. Is everybody okay that if I say the sum from k equals infinity to 1 is the same as the summation from 1 to infinity? I'm just adding up the same terms, just in a different order. I didn't change anything. I can also take this minus sign in the exponent and bring it inside. To make this 2 to the minus 1, make this as e to the plus 1. And now I'm almost got my alpha to the k sum, but I need a sum from 0 to infinity. Well, let's make a sum from 0 to infinity and then subtract off the k equals 0 term. That's not cheating, right? So are you okay that if I take this sum from 1 to infinity is the same as taking the sum from 0 to infinity and subtract off the 0 term? That's all this is saying. The 0 term, k equals 0, is this thing raised to the 0 power, which is always 1. So I have a 1 minus this sum, and this sum I have a formula for. It's this thing over 1 minus this thing, and 2 to the minus 1 times z is the same as z over 2. But I got to keep my requirement to use that summation formula. This thing inside the expression, that alpha, had to have a magnitude less than 1. So you're going to keep that along. I'll combine these algebraically, I'll pretty them up, and we get z over z minus 2. And this gives me a region of convergence that z has to have a value greater than 2, less than 2, excuse me, less than 2 for this. 1/2, boom. And so here's the point of this weird problem. We got the exact same answer for h of z that we did on the previous page. Same h of z. The only thing that changed was the region of convergence. This one had a region of convergence plus 2. This one had a region of convergence inside 2. That's why we say the region of convergence now matters. Not only does it tell you where it's going to converge, but if you don't know both h of z and the region of convergence, you don't know where they came from. Because two very different sequences have the same transform. One causal, one anti-causal. And so it's imperative to specify both, or you don't really know what your original time function is. Now, we're going to not be too crazy about specifying region of convergence because we're going to be working a lot with causal signals, causal impulse responses, causal functions. So let's just agree amongst ourselves, if we don't talk about region of convergence, we're assuming we're talking about causal signals. Okay. But strictly speaking, I should tell you a region of convergence every time I give you a transform. And, as we just saw in that example, the shape of the region of convergence actually is dependent on the direction that your signal's going, left or right, causal or not, left-handed or right-handed. If you have an infinite h of n, and it's either causal or right-sided, meaning it keeps going on the right side, and stops and goes to 0 on the left side. So a causal signal would be that, like that, but we won't even restrict ourselves to causal. Even if it's non-causal, we'll let this beginning point linger over. It's going to have a particular shaped region of convergence. It's going to have a region of convergence that's all points outside of some minimum radius. If I have the converse case, if I have a sequence that goes backward in time for infinite length and cuts off and stops for all values n beyond some data, so that kind of like an anti-causal, or even one that starts over here that we would call a left-sided signal, that's going to have the opposite region of convergence. It's going to be from some radius inward. And if you have a function that goes to infinity in both directions, you get both restrictions, and you get a donut for region of convergence. It has a minimum radius and a maximum radius, and the only allowed values of z are inside the donut. And if you have a finite sequence, well, don't get lost in this picture. We saw this about 8 slides ago. This was a non-causal, finite-length signal. We found its Z-transform, and I don't want to repeat what we did. What I want to do is look at this answer we got and ask, is there any value of Z that I'm not allowed to use for, let's say, these two terms? Any values of Z that would make those two terms blow up? Positive, negative, fractions, anything that I can't use.
0.
I can't use 0. Z to the minus 1 is 1 over Z. Z to the minus 2 is 1 over Z squared. So if I use 0, it goes to infinity. Okay. So I have a finite length sequence, and so that says the region of convergence for this transform cannot include 0. How about these guys? Any value of Z I'm not allowed to use? Only thing I can't use is infinity. Okay? And that's the nature of finite length sequences. If they're finite length, then they're neither right-sided nor left-sided, so the donut collapses or expands, depending on how you look at it. You may be not allowed to use Z equals 0, and or you may not be allowed to use Z equals infinity, depending on if you have Z to the minus something terms or Z to the plus something terms. So finite length sequences, the region of convergence is all Z except Z equals 0 if you have non-zero positive n values, because that gives us Z to the minus n terms. And or Z equals infinity if you have stuff to the left of n equals 0, they're non-zero, because then we'll have Z to the plus n terms. So finite length sequences have a much larger region of convergence, pretty much everything except maybe 0 and infinity. Infinite length sequences, you're going to have to worry about some minimum or maximum radii. Okay, questions on that? Now we're going to get more sophisticated than that as we start introducing the ideas of poles and zeros and transfer functions, and we'll be able to relate those again to regions of convergence. As a matter of fact, it's going to become very easy to spot and find the region of convergence for a function directly from its Z-transform. But for now, let's stick with the strict definitions. And with 6.5 minutes left, let's derive some more so we never have to do it again. Okay? So let's plug and chug with the formula on a couple of Z-transforms, and then we'll read about a few more, and then we'll consider ourselves satisfied that we've seen enough Z-transforms. We could do it if we had to, but we don't want to do it anymore. Right? Deal? Okay. Let's try a few of our favorites here. If our input or our signal that we're transforming is a unit sample sequence, then what is the Z-transform of that? The sum from n equals minus infinity to plus infinity of our function times Z to the minus n. However, just like our finite length sequences, this is the most finite of finite length sequences. It only has one term at n equals 0. And that's x sub 0 times Z to the minus 0. And x sub 0 happens to be a 1. And Z to the minus 0 is also 1. So it's 1. That's my kind of transform. And is there anything in there to hint that there's any value of Z you could not use? Is there anything going to mess up my region of convergence?
0.
0? No, Z to the 0 is 1. I'm good. Yeah, so this is one of those transforms that the region of convergence is all Z. There is no limitation. There was no summation formula invoked that that had some limitation on it. There's no z to the minus anything that's giving me trouble in the transform. It's 1 everywhere, which is kind of a strange thought. It's a constant 1 for all z, all directions. But similar to the Fourier transform, as a matter of fact. Is that? Okay, how about, a pulse. What is the discrete time Fourier transform of a pulse? So what is this function? X of n is, what is it, u of n minus u of n minus capital N. What does that look like? U of n looks like this, and u of n minus n starts at n equals starts over here at n, right? All zeros. Oops, first one's an n. So I think if I subtract those, I'm going to get something that looks like a function that goes along here. And I think it's going to stop at n minus 1. Do you agree with that? So it's a finite length pulse. Or whatever n is. Okay. What's the z transform of that guy? Well, so what is this? This is our x of n's like delta of n plus delta of n minus 1 plus delta of n minus 2 plus a whole bunch of those delta of n minus capital N minus 1. That's where I get that last sample. Okay. Well, that's a 1, that's a 1, that's a 1, that's a 1, that's a 1. So I think this is going to give me a 1 plus z to the minus 1 plus z to the minus 2 plus z to the minus 3 plus dot, 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 all the way down to z to the minus, oops, z to the minus 1 I did over here, capital N minus 1. That's a sum from, let's call it k. K equals 0 to n minus 1, just so I don't mess up my notation, of z to the minus k. Would you agree? Okay. That's when we have to look up in a summation formula. There is one in books that says the sum from k equals 0 to, let's call it capital M, of something to the k. Well, that's a 1 minus alpha to the n plus 1 over 1 minus alpha, as long as alpha is not equal to 1, because in that case, it turns into m plus 1. So there is a closed form solution. There's no limitation on alpha, just I get a different answer here. And if I apply that to this, I think if I keep my nomenclature straight, I'll get a 1 minus z to the minus capital N over 1 minus z to the minus 1, right? Yeah, z to the minus 1. Either that or n. And it's this answer if z is not equal to 1, and it's this answer if z equals 1. which is voila. Now, and in terms of region of convergence, the only ones that are going to give me trouble because of these terms are z can't be 0. But I didn't pick up any other region of convergence requirements from this definition, so that's the only one I'm going to have to worry about. And it is a finite-length sequence. Okay. If you read in your book, you can see we also, well, we derived this one already, alpha Bn. Unit step is just a special case of that one. That's also a special case. There's n times, there's n times alpha, there's cosines and sines and exponentials. So some of these are derived in your book. Go ahead and look through those derivations. We'll have to take class time to do those. Next time what we'll do is pick up and talk about properties and transform tables and how to start using them. We'll do that on Friday.